Okay. Welcome back, everyone. So today it's my pleasure to introduce Jonathan Love, who is a postdoc at Leiden University, and he will be talking about the topography of isogeny graphs. So Jonathan, take it away.
Absolutely. Thank you so much for the invitation. It's really great to be here. Happy to be sharing this with you all. This talk is going to be a little bit strange or not very typical in that the focus is really not going to be on results. I'm not here to share any new proofs or new observations with you, although there will be a little bit of that. Really, the focus of this talk is going to be just a different way of thinking about or visualizing isogeny graphs that helps to summarize a lot of key features that these isogeny graphs have. So it's going to be very explorative. It's going to be very sort of just looking at pictures and trying to understand what they mean. So at any point, feel free to stop. I have the chat open so you can put in, Q for question or something, and feel free to stop, explore, whatever the case may be. I'm happy for this to be a very exploratory time. So without further ado, let's start by setting the stage. We're going to be working with, there we go, some isogeny graphs. So as we often do in this context, we're going to take two primes, one very large prime and one much smaller prime. I'm going to be having a running example in this talk where P is going to be 100,003 and L is going to be equal to 2. Using this data, we can define the supersingular isogeny graph GPL. The vertices come from supersingular elliptic curves over FP squared up to isomorphism. And from each vertex, there are going to be L+1 edges, each corresponding to a degree L isogeny, where we quotient out by saying two isogenies are equivalent if you can compose one with an isomorphism afterwards to get the other. This is a directed graph, but each isogeny has an arrow in the reverse direction, the dual isogeny, and so we can match up an isogeny with its dual and get an undirected graph. Of course, there are little issues around the curves with extra automorphisms, but essentially, this is how we define these supersingular isogeny graphs. And if we construct this graph with P equals 100,003 and L equals 2, we get something that looks a little bit like this. It's a mess. There are little bits of structure that you might be able to see, like that sort of loop, that lollipop sticking out the side, might sort of raise some interest. But aside from that, there's really very little we can say about the structure of this graph. And in fact, the reason that these isogeny graphs are so useful is precisely because they are messy. What I mean by messy, one feature is that they're called expander graphs or Ramanujan graphs, meaning that if you start with any point in these graphs and take a random walk, the probability of landing on any other point in the graph converges extremely rapidly to the uniform distribution. Another sense in which they are messy is that there is no efficient pathfinding algorithm, assuming you don't have any extra information. If all I give you is the coordinates of a starting point and an ending point, and I don't give you any endomorphism rings, I don't give you any extra points with their image, if I don't give you anything else, we don't have a good idea for how to find a path from A to B. And these features make it really good candidate for cryptographic applications. I'm not going to be talking too much about cryptographic applications in this talk. What I'm interested in is the reverse question. In the midst of all this chaos, is there some structure we can get our hands on? Are there any structures that we can identify within these graphs? And the key idea that we're going to be exploring is that the endomorphism ring of an elliptic curve determines the structure of the graph near that point. Now, this is a narrative that has come up in many, many papers and many, many results, and I won't have nearly enough time to address all of them in this talk. But just to say that this is a consistent narrative that has often been used to study these graphs, to study the counts of cycles, to study places in the graph that have fewer cycles than normal, et cetera, et cetera. It's a constant through line through the study of these graphs to use this endomorphism ring. In order to understand how this process works of using the endomorphism ring to study the structure of the graph, I want to give a brief primer on quaternions, quaternion algebras and orders. We're going to start with BP infinity being the quaternion algebra over Q, ramified at Pn infinity. If you don't have a lot of background with quaternion algebras, we can say something much more explicit in this particular case. So if P is 100,003, P is 3 mod 4. So in this case, we have a very explicit form for this quaternion algebra. It's a four-dimensional vector space over Q with basis 1 I, j, k, satisfying certain multiplication rules. I squared is -1, j squared and k squared are both minus p, and ij equals minus ji equals k. Using these rules, you can determine any other multiplication that you wish. Now, an important point here is the fact that the multiplication is not commutative, so this is not a field. There are a few primitives, a few basic notions that we can define on the elements in BP infinity. We can take an element alpha and conjugate it. This just means subtract the ij and k components. We can compute its trace, which is alpha plus alpha bar. It's just twice the real part. And we can compute the norm, which is alpha times alpha bar. And this turns out to be a rational number given by a squared plus b squared plus pc squared plus pd squared in this particular case. Let's just move those to the top of the screen. An important feature of the fact that the norm looks like a sum of squares is that the norm defines a positive definite quadratic form on this four-dimensional vector space. And associated to any quadratic form, we have an inner product given by 1/2 times the norm of x plus y minus the norm of x minus the norm of y. And when we expand everything out using the product form of the norm and simplify, what we find is that the inner product is actually given by the trace of x times y bar, all divided by 2. So what this says is that the norm gives us a way of measuring lengths, and the trace of the product gives us a way of measuring angles. So this is something to keep in mind that we'll come back later. Now, I've described sort of the vector space structure and the norm structure on this vector space, but what we really care about are lattices inside this vector space, and specifically lattices that are closed under multiplication. So an order in BP infinity is a rank 4 lattice inside this four-dimensional vector space that is a ring. So it contains 1 and is closed under multiplication. We say an order is maximal if there is no larger order containing it. Now, there are lots and lots of orders, in fact, infinitely many orders in any BP infinity. But we're going to define an equivalence relation by saying that one order is equivalent to another if you can conjugate one by another, meaning multiply by x on the left and x inverse on the right. An important observation about this is that it's the same as saying that O prime and O are isomorphic as rings. One direction is straightforward. So if you start with an order O and you apply conjugation, this preserves the addition and multiplication structure. So x, O, x inverse will be isomorphic as a ring to O. The inverse direction takes a little bit more work. Basically, the idea is that if you know that these two orders are isomorphic as rings, you can use the norm, which is defined in terms of the multiplication, to recover the norm structure, the length structure, the isometry structure on these lattices. And there's a classification that says that any isometry of BP infinity that fixes the rational numbers is given by conjugation by some element. So using this, you can go from isomorphism to equivalence. Now, there are infinitely many maximal orders, but only finitely many equivalence classes. Now, it is finite, but for very large values of p, the number is quite large. It grows linearly with p. So that's all the basics of quaternions out of the way. Now, where this comes in with elliptic curves is the following. Starting with a supersingular elliptic curve, we can define this endomorphism ring. So this is just the set of morphisms from the elliptic curve to itself that preserves the identity. And there are these operations that we can perform on this elliptic curve. Namely, we can add two endomorphisms by adding them the outputs pointwise, and we can multiply by composing. Now, this endomorphism ring, the reason it's related to quaternion algebras comes from what's known as the Dorian correspondence, which I will not state in full detail here, but a few consequences will be useful to us. The first is that the endomorphism ring is always isomorphic to some maximal order in BP infinity. Conversely, given any maximal order in BP infinity, it is isomorphic to some endomorphism ring of some supersingular elliptic curve. And the elliptic curve in question is almost uniquely determined. The only difference is that given an elliptic curve, you can raise all its coefficients to the power of p and get another elliptic curve with an isomorphic endomorphism ring. So you can have two elliptic curves that have the same or equivalent endomorphism rings. But that is the only way that you will ever get two elliptic curves that have isomorphic endomorphism rings. Finally, bringing isogenies into the picture, Often this is phrased in terms of ideals, but I don't really want to get too much into ideals in this talk, so I'm going to phrase it slightly differently and say that if you have an isogeny, then there is some way of orienting your orders in the BP infinity space in such a way that their intersection has index equal to the degree of phi inside each of the orders in question. Now, there can be many isogenies from E to E prime, all of different degrees. And for every isogeny, we should think of this as being there's a different equivalence, a different equivalent order, so a different way of orienting these orders in BP infinity that leads to a different size of intersection. So these O and O prime are not, there's no canonical choice. They can be moved around by isometries. And for each isogeny, there is some way of sticking them in BP infinity that leads to a particular sized intersection. I think I'm going to pause there for now. I've done the primer on quaternions and endomorphism rings. Any clarifications that people would like to make before I move on? Great. Okay. So the next thing that I want to talk about is about what's called the gross lattice, and specifically successive minima within this gross lattice. So this endomorphism ring, it's a lattice inside a quaternion algebra, which means that it's four-dimensional. So it has a basis given by four vectors. But one of these directions is very easily understood. Namely, given any integer n, you can just take a point on your elliptic curve and add it to itself n times. This gives you a map from E to itself. So the integers very naturally lie in the endomorphism ring. So if we want to study these structures, one thing that's very natural to do is just quotient out by the integers and land with something three-dimensional. And this is the basic idea behind the gross lattice. The construction of the gross lattice, intuitively, we should think about this as literally just take your entire four-dimensional picture and orthogonally project in the direction of the integers. So you're going from something four-dimensional to something three-dimensional. Now, if you just orthogonally project, you're going to end up with points that aren't in the original order. But if you scale everything by 2, then you end up with something that is still lying inside the original order. So starting with O, if I orthogonally project and then scale up by 2, I will end up with some sublattice of the original order, and that is called the gross lattice. You can define it in terms of this function here, 2 alpha minus trace of alpha. It'll take any point, and it will send it to some element of trace 0 in O. Just to visualize what's going on here, what I'm going to do is take some two-dimensional slices of this this maximal order. So hard to visualize 4 dimensions, but what we can do is take the two-dimensional slice, span by 1, and some other non-integer element. So here's 1, and here's, let's just say this is alpha right here. Now, what we find is that if we intersect O with this space, we get something that looks a lot like some order in an imaginary quadratic field. And if we take this element alpha and apply this 2 alpha minus trace alpha rule, we get an element beta. And I've labeled beta by a square to say that this is an element of the gross lattice. Now, in the case that trace of alpha is odd, then this gives you the shortest element in this lattice. But in the case that trace of alpha is even, so you could actually have an element of trace 0, very important to note that this element here is not an element of the gross lattice, but twice that vector is an element of the gross lattice. So this is sort of the method of starting with elements of the endomorphism ring and producing elements of the gross lattice. Any of these alpha along this line will all produce the same beta. Any of these elements along this line all produce the same beta. Now, an important computation is that if you have an element alpha such that Z adjoint alpha is a quadratic order of discriminant minus D, then in fact this element beta you produce is an element of norm equal to D. So what we find is that the gross lattice parametrizes embeddings of quadratic orders in the maximal order O in such a way that if the discriminant of the quadratic order is minus D, then the norm of the corresponding gross lattice element is equal to D. So what we're left with now is this three-dimensional sublattice. And 3 dimensions are a lot easier for us to visualize for whatever reason. So what we're going to do is consider a short basis for OT. And specifically, the short basis that we're going to use is going to be given by the successive minima. So beta 1, beta 2, and beta 3 are going to represent a basis for OT that are in some sense as short as possible. There's no vector shorter than beta 1. There's no vector shorter than beta 2 that's independent of beta 1. And there's no vector shorter than beta 3 that's independent of beta 1 and beta 2. These three vectors, we will say, attain the successive minima of the gross lattice. And their norms, d1, d2, d3, will be called the successive minima. I'm going to throw a few warnings up here on the screen because there's a few ways that this differs from the standard definition. The first is that I'm using successive minima to refer to norms, so values of a quadratic form, not lengths. So if you're used to thinking about successive minima in terms of lengths, you should think of the di's as being the squares of the successive minima in terms of lengths. The other warning is that this definition I've given here in terms of a basis only works for dimensions at most 4. Once you go to dimension 5 or above, things break down. There might not exist a basis with these properties. So the proper definition of successive minima looks a little bit different. But in dimension 3, everything is nice. We actually get a basis of vectors that are as short as possible. Now, the gross lattice is some 3-dimensional lattice, and its isometry type actually determines the maximal order up to equivalence. And this is a fairly classical construction. Namely, you take the gross lattice, you consider its dual lattice, and then there's this operation called the even-Clifford algebra construction that recovers O. It allows you to turn the ternary quadratic form into a multiplication structure. So that's very well understood. A more recent result is that you don't actually have to know the entire isometry type of the gross lattice. It's enough just to know its successive minima. If you know the successive minima of the gross lattice, this uniquely determines the maximal order up to equivalence. A version of this was proven by Chevyrev and Galbraith under quite a few little technical conditions. And Eyal Goren and I recently showed that we can remove those technical conditions and prove it for all maximal orders in BP infinity. This is an important point. What this means is that given an elliptic curve, a supersingular elliptic curve, we can take its endomorphism ring and its corresponding gross lattice and compute the 3 successive minima. So this gives us a sequence of 3 integers. And this gives us a label for the elliptic curve. And it's almost unique. The only 2 elliptic curves that will have the same label are if there are 2 elliptic curves that are Frobenius conjugate to each other. Up to that, every elliptic curve will have a distinct label. So I just want to quickly run through an example of how we can compute these successive minima. So once again, the example that I have in mind is P is 100,003. So we have these multiplication rules as written down on the screen. Now, if we take the elliptic curve over FP with J invariant 1728, then the endomorphism ring happens to have the following form. So it's generated by 1. By I is this extra automorphism that the curve of J invariant 1728 has. And then these 2 extra elements, 1 plus J over 2 and I plus K over 2. Now I want to observe that if we take this element 1 plus J over 2, multiply it by 2 and subtract 1, I get the element J whose square is minus P. And so that element is actually the Frobenius endomorphism, which exists because our curve is defined over FP. Now, because we now have a generator for O, we can apply this 2 alpha minus trace alpha map to compute generators for the gross lattice. So namely, I gets mapped to 2i, 1 plus J over 2 gets mapped to J. The real part disappears when you subtract the trace. And I plus K over 2 maps to I plus K. Now, there's some things you need to check, but this basis, 2ij, I plus k, turns out to attain the successive minimum. It's essentially as close to orthogonal as you can get. And so what this means is that d1 is the norm of 2i, which equals 4. The norm of j is equal to p. The norm of I plus k is equal to 1 plus p. And so we get a label for this elliptic curve, namely the point 4, 100,003, 100,004. We're going to do this for all supersingular elliptic curves over f 100,003 squared. Now, because the successive minima can be sometimes very small and sometimes much larger by several orders of magnitude, we're actually going to plot these in a log scale. So the picture that I'm going to show is going to be plotting actually log d1, log d2, and log d3. And this is the picture that we get. So this point up in the top corner here is the point for 100,003, 100,004. But there are many other points all spread out through this space. And unfortunately, it seems like we're not going to get a very smooth animation, so I'm going to sort of start and stop at various points. And I want to observe that as we rotate through this space, it appears that this set of points is very close to lying in a plane. Now, it doesn't exactly lie in a plane. So for example, if I pause right here, you'll notice that this area is kind of thick. So it's like close to lying in a plane, but it thickens around this very dense region. But it seems to be very close to lying in a plane. Aside from that, there's a lot of other structures. So for example, it seems to lie in this like triangle space. There's all these weird stripes in it. There's a lot of weird questions. What is the structure of this region? What is going on? And so those are some questions that I want to highlight. Why do these points appear to lie in a plane? What are the bounds of the region? What does it mean for some points to be in the sparse region or the dense region? My claim is that we can use this to study isogeny graphs. So I also want to ask the question, which of these points are connected by two isogenies? And then finally, what are the stripes? This is going to be essentially the outline of my talk, is exploring this figure and trying to understand the answers to these questions. Some of these have very straightforward answers just in terms of lattice geometry. If you just know how lattices of certain shape work, you're going to get the answer. Others depend in a more subtle way on the multiplicative structure of these orders, and I'll try to highlight that as we go through. So first question, why do these triples appear to lie in a plane, at least when you plot their logarithms? This turns out to depend on the fact that all of the maximal orders have the same determinant. So when I define a determinant in this talk, what I mean is I'm going to take the matrix of all inner products of the basis vectors. So if you're thinking about a determinant of a lattice as a subgroup of Rn, where the basis vectors are columns of your matrix, once again, like with successive minima, we're going to see a difference of a square. So if you take a lattice in Rn, and B is a matrix whose column vectors are the basis vectors of your lattice, then when I say determinant of lambda, what I mean is the determinant of B transpose times B, because that's how you get the inner products of the basis vectors. And that turns out to be the square of the covolume of the lattice. So just to keep in mind, whenever I say determinant of a lattice, I'm referring to the square of the covolume. But we can define this in terms of the inner product. Anytime we have an inner product structure, we can define this determinant. The language we use sometimes is the determinant of the Gram matrix of the lattice. An important fact is that maximal orders all have the same determinant. Namely, under this inner product I defined before, 1/2 times the trace of xy bar, the determinant is 1/16 times p squared. Now for any maximal order, the gross lattice lives inside the maximal order in a very precise way. Namely, if you take the gross lattice and take the orthogonal direct sum with the integers, you get an index 8 sublattice. And using this fact, we can actually show that the determinant of the gross lattice is 4p squared. So that's the important thing that will allow us to understand why d1, d2, d3 happen to lie in a plane, is because gross lattices of maximal orders all have equal determinants. Now, the other important factor is that if we take vectors attaining the successive minima, they will be very, very close to orthogonal. So d1 times d2 times d3, remember this is the product of the squares of their lengths, is going to be very, very close to the square of the covolume, or the square of the volume of a parallelepiped. So d1, d2, d3 should be very close to the determinant of the lattice. We can be more precise, and in the case of these rank 3 lattices, we can prove that this product of successive minima is bounded strictly between, or is bounded between, up to less than or equal to signs, between 4p squared and 8p squared. And this is where the plane comes from, because when we take logarithms of this equation, we find that the sum of the logarithms of d1, d2, and d3 is very, very close to the log of 4p squared. There's going to be a little bit of error, so there's not going to lie precisely in this plane. There's going to be a little bit of wiggle room. But essentially, because p is so large, it looks like these triples actually do lie in a plane when you plot them in the log scale. Now, the advantage of this is that it means we can now project, and we won't be losing too much information. So we're going to take this whole picture in 3D space and only plot d1, d2. One word of warning is that d1 and d2 do not uniquely determine the maximal order. So there are examples where you can have two different maximal orders with different successive minima, but where D1 and D2 agree. So this is losing a little bit of information. There are certain points in here that actually came from 2 points which are different in the D3 component, but just keep that in mind. The overall shape is going to be very similar. So what is the shape of this region? What is this region that we've constructed? Well, there's a few bounds that come immediately just from the definition of successive minima. So by definition, D1 is at most D2 and D2 is at most D3. So D1 is at most D2 tells us that, we're plotting D1 against D2, so you have to be at least above the line where D1 equals D2. We also need D2 is at most D3. Now, D3 doesn't appear in this picture, but of course, remembering that D1, D2, D3 is at most 8p squared, this allows us to find an inequality relating D2 to D1. Namely, D2 squared is at most 8p squared over D1. Now remember, we're in the log-log plot, so this square root of D1 is going to look like a line of slope minus a half. Now you might object and say, okay, well, this isn't a very sharp bound. There's this big gap. And the reason for that gap there is actually because, as said before, for most lattices, you're going to be very close to an orthogonal basis. So most of the time, D1, D2, D3 is actually going to be closer to 4p squared. So essentially, we should think about this dashed line as being the true upper bound of this region. And this is coming from D1, D2, D3 equals 4p squared. And then you're just going to get some points that leak above this because they're not exactly orthogonal. But for now, we'll just leave that upper bound there. Now, these bounds hold for any lattice with the fixed discriminant 4p squared, fixed determinant, sorry. But we see that there's this huge blank region down here that we'd like to get rid of. And this comes from the multiplicative structure. Because O is closed under multiplication, we can show that D1 times D2 must be at least greater than or equal to D3. And this essentially comes from the fact that you can take two elements of the gross lattice and multiply them together and get a new independent element. Not necessarily in the gross lattice, but up to small modification, you can get something that lands in the gross lattice. And so again, using the fact that D1, D2, D3 is greater than or equal to 4p squared, we get this lower bound on the data, that D2 has to be at least 2p over D1. And so we get this nice triangle. One observation I'd like to make is that this point right here, where orange intersects blue, that corresponds to the place where D1, D2, and D3 are all equal, because the blue line comes from D1 equals D2, orange comes from D2 equals D3. So what we see is that most supersingular curves are trying to concentrate in the region where D1, D2, and D3 are as close to each other as possible. The further away you get from this point, the more stretched out the basic parallelogram or parallel pipe it is. So that's essentially what's going on with this structure here. Now, so far I've only plotted points, but now I want to look at how they're connected by two isogenies. And this is what happens if I take all supersingular elliptic curves and try to connect them by two isogenies. And it is a bit of a mess, but there are some strange structures going on in this picture that I'd like us to point out. For instance, we might notice that there are a lot of vertical lines, there are a lot of horizontal lines, and there are a lot of 45-degree diagonal lines. There are also a lot of loops going along this one diagonal here. And so a few questions that we're going to explore are, how long can these edges be? Why are there so many edges of particular shapes? What do these correspond to? What is the meaning of these edges? So just to get a little bit of a better feel for it, I took some random points in this graph and looked at their two isogeny neighbors. So starting with this elliptic curve, these are the D1, D2 labels of its two isogynous neighbors. Here's another example. Starting with this point here, you get that point, and that point are all two isogynous to it. Going up in the top corner, this point here is two isogynous to itself, and also there's two different two isogenies to this point down here. And here's an example on this sort of second strip where you have a map to itself and then one vertical and one horizontal. So this is the sort of structure that can happen. So how do we explain these behaviors? So as mentioned before, isogenies correspond to there being some way of organizing these maximal orders in space in such a way that they have a common index 2 sublattice. And this is the core feature of where we get these particular structures coming up in this graph. So if we start with O, take an index 2 sublattice, and then take some other lattice, which is an index 2 superlattice of that index 2 sublattice, we should try to imagine what are some ways that we can do that. So for example, what we can do is we can start with a basis and then double one of the basis vectors and have one of the other basis vectors. This is one very standard way of getting two different lattices with a common index 2 sublattice. So in moving from O to O prime, we can take the shortest vector and replace it with twice itself or half itself. We can take B2, beta 2, and replace it with twice itself or half itself. Or we can do any other number of things. There's lots of index 2 sublattices. It's not necessarily going to be given just by one of these basis vector moves. However, the key insight is that when you move to an index 2 sublattice, the norms of the shortest and second shortest elements of the basis can't change by more than a factor of 2. Which means that when we plot things in this log-log plot, the distance, the horizontal distance between 2 points that are 2 isogynous can never be more than log 2. And the horizontal distance can never be more than log 2. So you will never find an edge in this graph with a distance greater than log 2. And this is something that we observed when we were looking at all these examples, is that for each point, you're never going to see an edge that goes like from deep in the heart of this dense region all the way up to this sparse region. These isogenies seem to have relatively short edges, and that's what we've found here. If 2 points are close in the 2 isogeny graph, then they are also close in the successive minima space. So the successive minima space is in some sense capturing isogeny distance. So once again, I'll just quickly go through an example. So this point here has label 207, 3895, 50248. So that means in particular that there is an element of norm 207 and no shorter element. Now there is this loop, and I want to emphasize that in this case, this is not an isogeny from the curve to itself. This is not an endomorphism of degree 2. This is an isogeny from the curve to its Frobenius conjugate. You can't see that from this graph structure, but that is what's going on in this case, is that because E and EP correspond to the same label, it looks like you get these loops because you have a map from E to its conjugate. But also, you have these two other index sublattices, one obtained by preserving beta 2 and sort of taking an index 2 sublattice in the other direction, and one obtained by preserving beta 1 and allowing some change in the remaining directions. And so that's how you get these vertical and horizontal lines. The next question that I want to explore is this fact that we have a very dense region over here and a very sparse region over here. And it would be helpful to understand what this sparse region represents. Now, one of the reasons that the points are so dense here is the fact that we're doing this with a log scale. So as I go to the right, D1 just changes much, much faster. So of course, we're going to get many more points in this region of the graph. But is there some interpretation? Is there some understanding of the structure of what this left part of the graph looks like? And that's what I want to talk about next. So these are going to be the points with small d1. Now, I mentioned earlier in the talk that elements of the gross lattice parameterize embeddings of quadratic orders with discriminant minus d. So let's take this vertical line right here. So this is a vertical line with d1 equals 4. And so the existence of a point on this vertical line means that for this corresponding maximal order, there's a copy of the quadratic order with discriminant minus 4, namely z adjoint I, living inside this maximal order. Likewise here, so there's a line at d1 equals 11, one at d1 equals 15. Here's one at d1 equals 16. So the quadratic order with discriminant minus 16 is actually z adjoint 2i. So for each of these lines, 4, 11, 15, 16, 23 that I've drawn, I get embeddings of these various quadratic orders, z adjoint I, z adjoint 2i, or ones with various different discriminants. I highlighted this line d1 equals 23 because here we actually see 2 points. So these are 2 different maximal orders that both have a copy of z adjoint 1 plus root minus 23 over 2 in them. So that's one way to think about what's going on with these points, is that for each vertical line, we have an embedding of some quadratic order of small discriminant. A natural question arises, okay, of these sparse points, of these points with small d1, which of them are connected by 2 isogenies? So what I'm going to do is start now with this original point that we took, the top left corner. So this is 400,000 and 300,004. I'm going to take 5 steps in the 2 isogeny graph and see where I end up. Now I want to observe that even after 5 steps, there's a lot of these points in the sparse region that I never reach. So from this point with d1 equals 4, I get to a point with d1 equals 16. So that's this point here is 16, 25,003. Take another step and I land on a point with d1 equals 64. Another step and I land on a point with, there's actually 2 points that are very close to each other, with d1 equals 256. So what we'll observe is that each step I take multiplies d1 by 4. What's going on here is that starting with z adjoint I get to a copy of z adjoint 2i, z adjoint 4i, z adjoint 8i. At each, z adjoint 16i, my bad. So at each step, I'm changing the embedded order, but I'm not changing the quadratic subfield generated by each of these orders. We can see the same thing starting from this point with d1 equals 11. So here we have a point with d1 equals 11, and then we reach these 2 points with d1 equals 44, and then these 2 points with d1 equals 16 times 44, or 16 times 11, which is 176. Here's another example. So these are the 2 points with d1 equals 23. One of them has a loop to itself. But then 2 isogeny takes them to d1 equals 4 times 23. And then another step takes them to 16 times 23, and so on. The observation that I want to point out in all of these examples is that starting from this point in the top left, the steps I take only move me down and to the right. I never backtrack. Only once I've passed this red line and I sort of land in this messy region, only then can I then come back up past this red line. Now, it turns out that each of these examples I've drawn is actually an example of an isogeny volcano. So in this case, it's a little bit weird to look at this, but these 2 points with this weird loop is actually, in the true isogeny graph, a 3-cycle. What happened is that these 2 points in the 3-cycle are Frobenius conjugates. So when we map into the successive minima space, they map to the same maximal order. So these 2 points map to the same point here, and this edge becomes a loop. So that's why we get this structure here. But aside from that, aside from the fact that we're sort of gluing these 2 branches together, this entire structure, all the way down past the red line, is just an isogeny volcano. We have a cycle, which, if you know much about oriented isogeny graphs, this cycle comes from the class group action of z adjoin 1 plus root minus 23 over 2. And then we have these isogenies going down and to the right. And each step we take increases the conductor of the optimally embedded quadratic order. And what we see is that we keep going down and to the right until we're past the red line. What this means is that if I want to go from one point in the sparse region to another point in the sparse region, corresponding to orders with different subfields, non-isomorphic subfields, the only way I can do that is to first go into the red region and then backtrack and come back. So starting from the point with d1 equals 4, I can go to 16, 64, 256, land myself in this messy region, take a few more steps, and then eventually find my way back. There's no short path from 4 to 11. Any path to a different volcano must first descend into the depths of the isogeny graph. And this is an interpretation of a result that I proved in 2020 with Dan Boneh, which is that if you take any value of m, such that 4m is significantly smaller than 2 root p, then all of the supersingular curves with an embedded quadratic order smaller than 4m partitions into one set for every fundamental discriminant corresponding to an imaginary quadratic field that embeds in BP infinity. What we get is that within these set, if you have 2 points within the same set, there is a short path that connects you from one to the other without leaving this region. But if you have elliptic curves in 2 different sets, the shortest isogeny from one to the other takes a very long time. What this is saying is that to the left of this red line, in this what I'm calling the sparse region, this is literally just a disjoint union of isogeny volcanoes. The entire structure of this isogeny graph, it looks like a mess just because they're all overlaid on top of each other, but that is exactly what's going on here. Up to gluing Frobenius conjugates together, we can completely understand the structure of the graph to the left of this red line as a disjoint union of isogeny volcanoes. And the only way you can get from one to another is by first descending into the chaos of the dense region and then making your way back up. So that's the sparse region. They're just a bunch of volcanoes that don't meet. The last thing I want to talk about is these stripes. So we look at this picture and we see that there's these sort of these lines that seem to be separated into bands. Can we interpret these somehow? What is going on with these stripes? Now, these stripes come from what I like to call a rigidity law for gross lattices. So 3D lattices with a fixed determinant can have lots of different structures. But if you're coming from the gross lattice of a maximal order in BP infinity, there are very strong constraints on the shape that the gross lattice can take. Specifically, there's this proposition which a version of this was proven by Kaneko in 1989, but this is a slight rewording of it, a reinterpretation of it that's easier for us to apply. And what it says is that if we take two elements in the gross lattice and consider the rank 2 sublattice they generate, the determinant of that rank 2 sublattice, it has this explicit form, and it will always be a positive integer multiple of 4p. Another way of saying this, again, when we interpret what determinant of a lattice means, this means that if you take any parallelogram with vertices in the gross lattice, the square of its area, or the squarea, I might call it, is going to be a multiple of 4p. Now, just hearkening back to earlier in the talk, I mentioned this theorem with Eyal Goren that the successive minima of OT determine the isomorphism type of the order O. And what I want to emphasize is that this proposition is really the key input to this result. Because what it says is that if all you know is the successive minima, so that's just norm information, all you know is the norms of certain elements in the gross lattice. But given the norm data, you can learn something about the angles between these elements from this constraint, that the difference between the product of the norms and the inner product squared must be a positive integer multiple of 4p. And so that key insight is what allows us to recover the full isometry structure from just the successive minima. Now, how do you prove this result? I won't go through the full proof. It's a fairly straightforward but tedious computation. The idea is starting with beta 1 and beta 2, you can form this lattice 1, beta 1, beta 2, and their product, beta 1 times beta 2. The first observation is that this is a sublattice of the full maximal order, and so its determinant must be an integer multiple of the determinant of O. Secondly, because it has such a nice, easy to describe form, we can actually compute the determinant of L explicitly and relate it to the determinant of the 2D lattice, beta 1, beta 2. And by relating the determinant of the large lattice to the determinant of the smaller lattice, we obtain the desired result. Now, how does this result tell us anything about the stripes? Well, the idea here is that if beta 1 and beta 2 attain the first two successive minima, I've already said before that this means that they must be close to orthogonal. And the math that I have on the screen is just sort of giving some quantitative measure of what that means. Explicitly, because beta 2 attains the second successive minimum, beta 2 plus or minus beta 1 must be at least as large in norm. And so when you expand that out and do some simplification, you find that the trace of beta 1 times beta 2 bar, in other words, twice the inner product, can't be larger in absolute value than the norm of beta 1. So as long as the norm of beta 1 is not too big, it tells us that the trace term also can't be too big. So what we can conclude is that this expression here is what appears in Kaneko's proposition, this being a multiple of 4p, but the trace term being very small, tells us that d1 times d2 will either equal 4p itself or be just barely larger. So up to a very small error, d1 times d2 is a multiple of 4p. And that is where these stripes come from. Each of these stripes is the line d2 equals 4p times something divided by d1. This is just saying that d1 times d2 is equal to 4pn or maybe slightly larger. And you see that, especially for small values of d1, this is a very, very good approximation. And as you move to the right, the approximation gets worse and worse. Now, there's one more thing that one can say about these stripes. So I'm going to sort of briefly say that before I bring this to a close. So one nice subgraph of the supersingular isogeny graph is called the spine. So this was defined by a group of authors in this paper, Adventures in Supersingular Land. And the spine is just the subgraph induced by the curves that are defined over fp. So in general, they're all defined over fp squared, but there's going to be this sort of thin region in which they're defined over fp. Now, there's this very nice result by He, Korpal, Tran, and Vincent that came out very recently that says that you can determine whether an elliptic curve is defined over Fp from its successive minimum. Explicitly, if E is defined over Fp, then the gross lattice must contain a rank 2 sublattice of discriminant 4p, and D3 is larger than or equal to p. On the other hand, if E is not defined over Fp, then there is no discriminant 4p rank 2 sublattices. All the sublattices have discriminant at least 8p. And in this case, when the rank 2 sublattices are large, D3 is actually quite small. So there's this gap both in the rank 2 sublattice discriminants and in the size of D3 that tells us that the spine has this strict separation from the rest of the isogeny graph in the successive minima space. So what this means for us is that this bottom stripe is exactly the set of all supersingular elliptic curves defined over Fp. Now, I've colored them 2 different colors just to say that even for being defined over Fp, there's different orders that can be embedded. This plot just shows that they're sort of mixed together in weird ways. It turns out that D3 does allow you to distinguish between these 2 optimally embedded orders. But if you're just looking at D1, D2, it's a little bit hard to tell them apart. But that's something very nice, is that this lowest stripe exactly tells you where the spine of the isogeny graph is. Now, I just want to highlight a connection. So I think I saw Eli in the audience, and I was chatting with him at one point about this result he had about short cycles in these isogeny graphs being disproportionately occurring along the spine. And I'm calling this out because I think it's very closely related to this result of He, Korpal, Tran, and Vincent. Because what this result says is that if you're along the spine, then the gross lattice of the endomorphism ring has rank 2 sublattices with very small determinant. In other words, this means that the endomorphisms are actually more tightly packed than they would be for a typical supersingular elliptic curve. So both of these results, though they're proved in very different ways using very different tools, they're addressing the same phenomenon, that the spine has more small degree endomorphisms than a typical supersingular elliptic curve. So a question that I want to ask is, what is the exact relation between these 2 results? Can we use one to prove the other? It seems like there's some deeper meaning behind them both, and it'd be interesting to explore what exactly that is. Okay, so I'm going to bring things to a close now. The summary is that if we plot this supersingular isogeny graph according to D1, D2, we get to see lots of really interesting features of the supersingular isogeny graph. So first of all, this gives us a consistent way of plotting the isogeny graph, regardless of p, because the only thing that changes in the shape is the scale. It essentially grows like log p. So if we divide by log p, we can plot all supersingular curves over any p within the same triangle. There's this region to the left that captures curves with small non-integer endomorphisms, and that's just a disjoint union of volcanoes. Very easy to describe. We have this bottom stripe where D1 times D2 is as small as possible, and this is exactly the spine. So we can identify all these features, these curves with small non-integer endomorphisms, and the spine within this successive minima space. And finally, we have the fact that L isogeny curves are close to each other. And as you take P to be extremely large, this actually gets stronger and stronger. The distance within this graph, compared to the size of the whole set, is going to get much, much smaller. And so paths in the isogeny graph will actually look like little, essentially like Brownian motion walks, tiny little steps. I'm going to briefly end with a few open questions. The first one, it's possible that this result exists in the literature somewhere. I only asked this question today. So I just put this slide in today, so I haven't done my due diligence to check if it's been answered. But we come back to this observation where in this picture, we have all these loops along this second stripe. And recall that the second stripe corresponds to maximal orders that contain a rank 2 sublattice of determinant 8p. And I also pointed out that these loops correspond to having a degree 2 isogeny from E to its Frobenius conjugate. Now this bottom stripe actually corresponds to isogenies of degree 1 from E to its conjugate, in other words, isomorphisms. And so this raises a natural question, which is it true that there is an isogeny of degree L between a curve and its conjugate if and only if the gross lattice has a rank 2 sublattice of determinant equal to 4LP? Not sure. I'll just leave that as an open question. Happy to hear thoughts on that. A few other open questions. This was all very theoretical. Is it possible to actually take advantage of these structures without knowing the successive minima of the gross lattice to begin with? The answer is yes in some cases. So this is part of my joint work with Dan Boneh, was that we can produce these algorithms to detect whether you're in the left end of this picture, whether you're in the sparse region. And once you know you're in the sparse region, to compute the full endomorphism ring. So there are ways that we can sort of latch onto and get a hold of certain regions. But if we're in other regions, are there features that we can lay hold of? Other questions, is there some simple criterion to determine when a triple of integers happens to be the successive minima for the gross lattice of a maximal order in BP infinity? There are some simple criterion that are necessary, and we have an algorithm that we can sort of push through, and if it's successful, it produces the corresponding maximal order. But in general, I don't have sort of a nice numerical criterion that will tell you this triple corresponds to an elliptic curve. And finally, to what extent can this picture be generalized to higher dimensional isogeny graphs? So this was still just working with supersingular isogeny graphs of elliptic curves. But of course, we're very interested in isogeny graphs of higher dimensional abelian varieties. And these also have endomorphism rings lying in this very nice algebra. And so is there a similar sense in which we can compute successive minima and learn things about the abelian varieties in question based on the sizes of their relative successive minima? So that's all I'm going to say for today. Very happy to be here. I'm happy to take any questions.
Thank you very much, Jonathan. That was an excellent talk. As always, you can ask questions in the chat or just unmute. I will be so rude as usual and just ask the first question if anyone else get to. But I just like one thing you said at the end. Did you say that you had like an algorithm for taking 3 successive minima and computing the corresponding order?
Yes. So I'll briefly outline this. This is a combination of several results. The first is my result with Eyal, where we show that the successive minima do determine the order up to isomorphism. The steps involved in that are starting with the successive minima, use the Kaneko constraints to determine what the possible angles are. And once we've written down some finite list of all possible angles, we can sort of check them explicitly and find that only certain ones satisfy all the constraints. So there is an algorithm that takes a triple of successive minima, and if it comes from a maximal order, it will successfully produce a gross lattice of the right, or a 3D lattice of the right determinant. From there, you can then do this even Clifford algebra construction to recover the maximal order, and then there are existing algorithms that, given a maximal order, will find an elliptic curve with that endomorphism ring.
Yeah, that's cool. But so the first step is probably like exponential time for or linear NP, I guess, or no? Or is this really efficient?
No, I think this is an efficient algorithm. The step of
really?
going from the triple to the isometry type of the gross lattice is very, I think it's logarithmic NP. I'll have to double check, but it's a fairly straightforward algorithm. Yeah.
That's very cool. So then somehow like, yeah, okay, that's very interesting.
The issue is that if you're trying to search for a triple that comes from an elliptic curve, you might have to search through a lot of triples before you find it. So you have to sort of be lucky, and that process I think will take exponential time, is my suspicion. I don't think there's a good way of finding such a triple without going through and checking them all and then happening to land on the right one.
Yeah, that makes sense. But still, like then somehow if you wanted to store a quaternion order, you could just store the successive minima and then recompute the order once you need it.
Yep, that's absolutely
very cool.
Yeah, that should be very efficient.
Very cool. I didn't know.
So I see a hand, but I also see a question. I'll answer the question in the chat first. Yes, we do know how sparse the sparse region is. Essentially, so as you sort of move to the right, what you're doing, so I think I briefly mentioned that these 2 points right here, for example, of discriminant 23, these come from, so there are actually 3 supersingular elliptic curves there, and they come from the fact that the class number of z adjoin 1 plus root minus 23 over 2 is 3. And so as you sort of move to the right, the number of points you encounter is literally just a sum of class numbers of all of the orders that have embeddings in this BP infinity. And so we have asymptotics for the size of sums of class numbers. Very roughly speaking, as I take d to the right, it will grow roughly as d to the power 3/2. But of course, you can be as precise or as imprecise as you want with these asymptotics. But yes, we do have a very good understanding of sort of at each point how many new points show up. I guess Mark Hoban has a hand.
Hey, Jonathan,
sorry.
can you hear me well?
Yeah, I can hear you. Okay,
perfect. Yeah, so one question about your first open problem about whether curves have an L isogeny to their Frobenius conjugate. Yeah. So I think for large L, the first assertion should be true. Do you know if the second one is also true for arbitrarily large L?
I believe it is. For probably actually a similar reason, which is that as you increase the discriminant, the determinant of the allowable rank 2 sublattices, I don't think I can come up with the answer right now, but essentially it will have something to do with the fact that there's a theta function that captures the number of rank 2 sublattices of each discriminant, and those coefficients will grow rapidly. So it should.
Yeah, okay. Yeah, that's right. Indeed. Yeah, I agree actually. I think there should be some kind of modular form where you can prove the coefficients are at some point will be non-zero.
Exactly. Yeah. So I don't know this off the top of my head, like this will require checking, but I believe that should be doable. So very good question. Yeah, this is definitely something worth checking.
I had another question about the red line that you drew between the dense and the sparse region.
Oh, the red line, yes.
Yeah. Do you have an explicit description for this division?
Yes. So this red line is the line d1 equals 2 root p.
Okay.
Yeah. So yeah, d1 equals 2 root p.
Okay, perfect.
Yeah. And the reason that comes up is just because if you try to make it any larger, then this disjointness of these sets starts to fail. The only way we can prove that these sets are disjoint is if you cap it off at 2 root p.
And in general, maybe L root p then? Or not true. Like if you take L isogenies where L is bigger than 2.
No, so this actually does not depend on the value of L. So notice that the isogenies that come up here, you can actually take sort of a range of values of L between 1 and 4 over pi root m. So in fact, even if you allow 2 isogenies, 3 isogenies, 5 isogenies, all isogenies up to 4 over pi root m, it will still be the case that these sets will be disjoint, even if you take all of these isogenies at once. The 2 root p comes more sort of, it has more to do with the lattice structure. So it's sort of more inherent to the lattice geometry. And it comes from the fact that if you allow yourself to go further than that, then you essentially, I'll just say this, the 2 root p is the square root of Kaneko 4p. So the 4p that occurs here, that's why the 2 shows up. So it's not, it has nothing to do with L, it has to do with something intrinsic to the lattice geometry.
Okay, perfect, thanks.
Are there any more questions?
Yeah, I have a quick question. Sorry, I also saw a hand. Didn't mean to jump in before someone. But Jonathan, you said that the exceptions where like D1 and D2 don't classify the order are rare. But do you know anything about like whether you can quantify like how many collisions you get when you forget D3?
Yeah, so they're not actually that rare. Like I said they were rare, but they really aren't. So in this example here with, there's 4,206 maximal orders. And even just in here, there's 738 pairs where D1 and D2 are equal. So calling them rare, I think, was a bad move. Like that was not accurate. Because because 738 is a pretty significant chunk of 4,000. I don't know asymptotically how this grows, like whether the proportion goes to 0 or the proportion grows. That I just don't know. Really what I wanted to say was not so much the rarity of it as much as the, even if 2 points happen to go to the same point, their location within the bigger structure is what matters more than whether you can like tell points apart or not.
Gotcha.
So good question. That was a mistake on my part in saying that. Okay, I see a hand from QDM Guido.
Sorry, maybe a small one on the at the very end of your talk. You said that using the graph structure, you can recover whether a curve is in the sparse zone.
Yes.
And yeah, how do you do that?
Right. So essentially the way the algorithm goes is as follows. First, or okay, I'll put it this way. There's an algorithm that if it succeeds, it will find, or I'll put it this way. If you have a non-integer endomorphism of norm at most m, then it will find it in time at most m, polynomial in m. If you don't, the algorithm will just run forever, and there's no sort of failure condition. So that's the first thing I want to emphasize. And essentially, the way it works is just you start with this point, and you do a breadth-first search through the isogeny graph. And, okay, sorry, first, before that, using this classification, okay, so using this classification, for each d up to a certain point, that's a fundamental discriminant, we can compute an explicit elliptic curve that has that as its endomorphism, that has an endomorphism ring with that inside. So this just comes from CM theory. So you can compute Hilbert class polynomials. The roots of the Hilbert class polynomial will be the J invariants of elliptic curves over number fields that have a quadratic order of, sorry, that have Cm by a quadratic order of discriminant minus d. So there is a way of, for each of these fundamental discriminants, producing a Cm elliptic curve with Cm by that order of discriminant minus d. For each of these, we can reduce it mod p and find a supersingular J invariant with an element, or with a quadratic order of that discriminant in its endomorphism ring. So far, does that make sense?
Yeah, of course.
Okay. Yeah. So
for
basically,
large D, maybe it requires some time, right?
Yes. So the key fact that makes this work is that as m grows, the time it takes to compute d also grows, but it does grow polynomially with m. So the process of computing these Hilbert class polynomials, I don't remember what the exact bound was, but it's something like m to the 6. So there's some polynomial time algorithm that it takes to compute the Hilbert class polynomial and find its roots. But of course, as m gets larger and larger, so certainly if you take m to be, size some power of p, this isn't going to work. This only works if m is up to like maybe 1,000, 10,000, something like that.
But instead, is it so what you said before is like if say 2, so the isogeny degree splits in the small order, then it's easy to recover. You're saying the order, but if it doesn't, maybe it's somewhat harder, right? Or
can you repeat that? Sorry, I'm not sure I quite heard.
yeah, is it? Yeah, but instead, so from the order to the graph, I kind of see it. The direction that I find interesting is from the graph around the point to the order, especially in the case where 2, say, or anyway the degree of the isogeny does not split in the order, maybe.
I see, right. Yes, of course. So basically the idea there is that we can start with this sort of basic generating set of elliptic curves, one for each of these t sub d sets, and use them to produce one sort of base point in each of these sets t sub d. What we then do is if we start with a supersingular elliptic curve, regardless of where it is in the graph, we start doing a breadth first search, and we just check at each step along the way whether we have bumped into one of these points.
Okay, nice, nice.
So
and thank you for the talk. So it was
yeah, no problem.
very nice.
Okay, maybe as it's past the hour, we'll stop questions for now. And if anyone wants to stay back a bit after to ask more questions, feel free. Yeah, so thank you, Jonathan, for the talk. It was really interesting. So in 2 weeks, we'll have the last talk of the season with Shai Levin from University of Auckland. And yeah, because of the time difference with New Zealand, the Isogeny Club talk will be a bit later than usual at 8:30, because there's a 12-hour time difference. So that was really the time that was possible. So yeah, we hope to see you all there. Bye-bye, everyone.
Thank you for hosting.